recording on this. Broad general question. In the movie, was there anything that really surprised you? Okay, just that whales had ancestors who were on land. Anything that surprised you about... So based on our last unit, which was how evolution works, was there anything in the movie that you thought, well, wait a minute, that doesn't fit with what I knew? Or anything that... Or did it all seem like, oh yeah, well that's how that would work? So I thought it was interesting. You know, they kept saying, but well, this species disappears from the fossil record, this species disappears from the fossil record. Did their tails change from swimming all the time?
The ones that had the bigger tails made it with the ones that had the bigger tails. And then
okay. The ones who had a flatter, bigger, broader tail might have been a little bit faster. Might have been a little bit better. A little bit more agile. Fewer of them got eaten young. Fewer of them got trapped someplace and died before they reproduced. Those broader back legs. So, anybody here run track? You run cross country, right? No? Why do I think you run cross country? You're running track this season? Okay. So some people are a little bit faster than others. This is no surprise to you. I'm going to tell you, there have been periods of my life where I was a runner. I run about as fast as a herd of turtles running in peanut butter. But I can run. It's just not pretty and it's not fast. If something big and toothed and vicious is chasing me, and I'm going to guess Robbie, guess who's going to survive? It's not me. Whatever the big tooth thing is will stop and eat me, and you will get away. You run on soccer, and soccer runs all the time. Soccer is like just running with a ball involved. Every one of us is a little bit different. In the case of those early, what were they called? What was that first whale ancestor we looked at? Pakicetus, good. In the case of Pakicetus, some of them had a better tail. Some of them had slightly better legs for swimming. Those faster ones made it. The ones with the skinny tails, the ones with the legs that looked really, really dog-like, who were, frankly, crappy swimmers, they didn't. They got eaten by something. They were preyed on. We did not get... So how many of you did finish up watching the movie last night on your own? Awesome. Okay.
I tried it
with your iPad. It wouldn't. Okay. They talked about Durodons moving towards the poles. So Durodon was the last species they talked about. It's the one that looked a lot like a modern what? Dolphin. Yeah, they're the ones who were very dolphin-like. About 16 feet long, really dolphin-like. And they said, Basilosaurus and Durodon are out in the big oceans, and there are predators. There's food down deep. Basilosaurus can't dive. They die out. Durodons are really agile, little sporty things. They're zippy. They can dive. They can do all kinds of stuff. And when big predators come along, the other thing Durodon can do, it was what the megalodon shark was the big predator. How many of you have ever seen Shark Week? This is, okay. I have not experienced Shark Week, but I have heard a lot about it. I have a friend who's obsessed with Shark Week. So tell me what Shark Week is.
It's just about sharks and all these different attacks and different things about sharks.
Okay, Moser, how much simpler can we make this? It's a week about sharks. That's why they call it Shark
Week. Just from different attacks, different stories to like evolution of sharks.
Okay. And I know, because again, reference Exhibit A, my friend who's obsessed, there was a special about Megalodon. The Megalodon! The, 40-foot shark, prehistoric shark. And this is what was preying on Durodons, the little dolphin-like things. It says, Durodon heads for the poles. Because Durodon's warm-blooded. They can keep themselves warm in cold water. There's good food up there. And then, so some Durodons probably had more fat than others. Some people store more fat than others. I have a dear friend. She's been my backpacking buddy for 20 years. Katie is a little bit taller than me. She's lucky if she weighs 105 pounds. She cannot store fat on her body. Doesn't matter what she does. She is just, and she is always cold. When she and I are backpacking, the big joke is, how many layers do you have on? How many layers do you have on? We'll be sitting out there in 40-degree fall evening, and I've got on a t-shirt and a fleece, and she's wearing a long john shirt, a wool sweater, a scarf around her neck, a hat, and a winter coat over it. So if she and I were Duradons, I'd be headed for the poles. She would not. So some of those Duradons had the ability to hold some fat on their bodies. Those who had a little bit better insulation did better at the poles. Those who stayed in the warm waters because they were just too chilly to go north or south, to go away from the equator, got eaten by megalodon. So it's about that variation again. Okay, so let's go back to this. Starting assumptions. So we talked about how evolution works. What we haven't really talked about is what the evidence for evolution is. And I thought the movie yesterday was a really good intro to that. What was the main source of evidence they were using in charting the evolution of sharks over history? What was their big piece of evidence? Fossils, yeah. They were looking at fossils of various shark species over the last, 50 million years or so?
Mainly like teeth fossils, those are the ones that would survive.
Yeah, they mostly had fossils of teeth. They had a lot of fossil teeth. They had a lot of fossil skulls. They did, though, have some fossil spinal columns because they were able to see how the neck bones changed. The tail is just part of the spinal column. So who here has a dog or has ever seen or petted a dog? Okay. Dogs' spines go all the way from the back of their neck all the way out to the tip of their tail. That is all spine. In a whale, that spine is the length of their body. And so they had some spinal fossils. They had things so they could see how the spine and how the tail had changed. Okay, starting assumptions when we start talking about evidence for evolution. The Earth is really, really old, 4.5, 4.6 billion years, depending on who you ask and how you add it up. There have been organisms of some sort on the Earth for most of that time. You made your timelines. I keep putting them back up. They keep falling down. But you know that for most of that 4.5, 4.6 billion year history, there have been things on the Earth. What were the first living things like?
One-celled organisms.
Yeah, they were like bacteria today. They were just single-celled organisms. And the other starting assumption we have here is that all organisms are evolving from an early one-celled thing. Why do we assume that? Because that's where the evidence points. I liked how in the movie, the scientists at several points said things like, well, this species did this, but we didn't believe it. Because part of science is just looking at the evidence and saying, well, what is the evidence telling me? And sometimes what the evidence is telling you is something that wasn't what you thought going in. Okay. There are that doesn't work. There. 3 major lines of evidence for evolution. Okay? And the first one is the one that was best highlighted in the film yesterday, which is the fossil evidence. So the fossil record is the first form of evidence of evolution. Who here has ever seen a dinosaur skeleton? Have you seen a picture of a dinosaur skeleton? Okay. We will be doing a trip for this class to the Carnegie Museum of Pittsburgh, and they have one of the best dinosaur collections in the country. And they have a fantastic display. And we try to keep the cost for the trip at like $20 or $25. We do some scholarship stuff if that's not reachable. We sometimes are able to make some arrangements, but they have got a fantastic fossil collection. You look at a dinosaur skeleton. If you're someone 500 years ago, 1,000 years ago, and you find a dinosaur skeleton, and you don't know anything that we know about past life forms and about Earth's past and about geology, what the heck is that? Clearly it's a dragon. What else could it be? Or a sea monster? I mean, what on earth else could something like that be? It's got to be. So, the fossil record is a record of past organisms. And what's interesting is that if we line them all up, we start to see subtle changes going from one thing to the other. About 5 years ago, maybe 6 or 7, no, more like 6 years ago now, the Carnegie, the museum that we're going to go to, did a real, and I've always liked horses, but I've never had horses. I raised rabbits in 4-H. I had horse envy. Though cleaning out my cages was easier than them mucking out their stalls. The Carnegie did a really cool traveling exhibit that was called Horse, an Evolutionary History. And they showed fossils of the earliest horses. And the earliest horses wouldn't have come up to your knee. They were horse-like creatures. So what connects that thing to a horse that stands way over your head? Well, the bones of their foot, some of the specific bones of their skull, 50 million years ago, show distinct similarities to the next thing. 35 million years ago, it's called Mesohippus. And gee, this looks an awful lot like this foot. Those feet look an awful lot alike. There are some differences, to be sure, but that kind of looks like it leads to that. Some of the bones have fused, but you can still see the lines where there were multiple bones. Well, if we go another 10 million years, 26 million years ago, this looks an awful lot like this. But again, you can see where some of the bones have fused. But all the bones are still there. And then this distinct structure in the front, this sort of toe, it looks like this skeleton is giving you the bird. It looks like it's flipping a middle finger at you. In a very real way, horses are flipping the middle finger at you all the time. Because this structure, which is like the middle finger of the bones of the horse hand, ends up giving rise to this. So one thing the fossil record gives us is this sense of stages, this sense of subtle changes over time. And you can see, if you look, that these things are related, but they're obviously different. And there are also some things in the skull, and I'm a little bit less versed on those. But you can see, if you look at those skulls, if you're a paleontologist, you can see subtle changes. So the fossil record gives us this record of change. Has anybody found a fossil? Okay, what'd you find? Okay, yeah. So, yes, sir? Okay, and also, so those are not fossils. Fossils are preserved. So what you found were artifacts of living things. So that deer skull tells you a deer was here. The bird bones tell you a bird was here and died. But fossils are older. Fossils are very often petrified. So fossils can be two things. They can be actual pieces of organisms. They can also be impressions in a rock, and I did not manage to bring in, I've got a really cool fossil that I found down at Beaver Creek. If you go down to the creek and you just walk along the creek and look at rocks, that's a great place to find fossils. Very often you'll see rocks that are split open and have fossils in them. So fossils form when something gets buried in fine sediment. There are some other types of fossils, but we're not going to get into those too much. The ones we're most interested in are the things that are either actual pieces of an animal or a plant, or an impression of them. And then there's this one. See that little one up there? What is that? Huh? It's an insect. What's it caught in? What is it? Sap? What'd you say, Kevin? It looks like it, doesn't it? It's tree sap, and if that's left for a few million years, it forms a gemstone called amber. If you saw Jurassic Park, they got the dinosaur DNA from where? From a fossilized mosquito, a mosquito that was trapped in amber. So fossils form, and the most common places that form fossils, swamps and shallow lakes, streams. Volcanic areas are great for fossils. You know why? Stuff gets buried. Stuff gets buried under volcanic ash. Now, a hot lava flow will just melt stuff. There's nothing left. But ash falling out of the sky will preserve things really, really well. So volcanic areas preserve things in ash. Streams, if something dies in a stream, very often mud and silt will cover it over. And the same thing happens in swamps and shallow lakes. There are gaps in the fossil record. Okay? There are gaps in the fossil record. Fossils don't show everything. So the things that are most likely to form fossils, things that have skeletons, things that are hard-bodied, things that have shells, turtles and sea creatures tend to form fossils. Woody plants. Your poor little bean plants, if we buried those in sediment, I do need to get those cleaned up. Those aren't woody plants. They're a soft stem. Would they form a fossil? What would happen if we buried those in sediment, in dirt? They'd just rot. Yeah. There'd be nothing left. There'd be nothing left in a few weeks, let alone in a few million years. Fossils give you a geologic time of death. So fossils give you a very broad idea of when something died in relation to other things. Fossils don't show soft-bodied stuff. Earthworms do not leave fossils. Earthworms don't leave fossils. Insects don't leave a lot of fossils. Amber's kind of an exception. And fossils don't show things that lived in deserts, usually. Mountains, places where it's dry and cold, doesn't lend itself to fossil preservation. So fossils don't show everything. So there are gaps in the fossil record, and some of those are because not everything gets fossilized. Where did they find the whale fossils?
It was in the desert.
It was in the desert. But had it been a desert at the time that those organisms were alive? No, it was an ocean. It was a shallow sea and then a deeper ocean. So when we say they don't usually show organisms that live in deserts, things that live in a desert today don't tend to get fossilized.
Like if a cow dies out there, it's probably...
Cow dies in the field, it's going to rot. Yeah, not likely to leave a fossil. A raccoon dying in a cornfield, not going to leave a fossil. It's going to rot. It's going to decompose. Something dying and getting buried in sediment in the edge of a stream today. Back when we were in the old building, and we could go down over the hill down to the creek, and we used to do that for environmental science. And one time we went down there to do some stream survey work, and of course my class found a rotting deer carcass, which some of them dragged up the stinky rotting skull with like the rotten brain stuff dripping out of the skull. It was awesome. They were so proud of themselves. That rotting deer left on the edge of that creek, the flesh would rot off it, but those bones might very well get covered in sediment and at some point become part of a sedimentary rock. And then 10 million years in the future, someone could find a fossil impression of that deer skull. But if that same deer died in the desert, it's probably going to dry up, and deserts don't form good sedimentary rocks.
So even if those skeleton got covered by sand, it's no way.
If it got covered by sand, and then that sand had pressure and moisture. So loose sand will just continue to blow around. To make a sedimentary rock, which is really that's where you usually find fossils, is sedimentary rock. To make a sedimentary rock, you need sand or silt, plus a little bit of moisture to kind of get it to start to glue together, and then you need pressure. So you need more layers on top of it. Loose sand does not make good fossils. So fossils don't show everything. It's not perfect. Okay, so how do we know? So they were saying, like, well, this disappears from the fossil record, and then this appears, and, oops, that should be law of, you can fix that. Oops, no, that's on top of older ones. They were saying, well, the Durodon fossils are 26 million years old, and the Basilosaurus fossils are 30 million years old, and Pachycephalosaurus is 75 million years old. How do they do that? So here's the neat thing. The Earth is a lot like a layer cake. And if we take layers of the Earth, well, the Earth is constantly forming new layers. So today, that stream bed that's right there, with silt on the edges of it, is a stream. But at some point in the future, something else may cover it up. Maybe it's a bunch of dead plants and animals. Maybe there's a cataclysmic event. If you heat your house with coal, you're heating your house with dead plants and animals from a cataclysmic event. And maybe then those get covered up by something else. Or maybe a glacier pushes material on top of those. The Earth has not always been as we see it. It changes. We sit here, it's a little bit hilly. You've noticed this, right? If you go further south, does it get hillier or flatter? It gets hillier. If you go further north, it gets flatter. The Appalachian Mountains, the entire mountain chain that runs through New York State, Pennsylvania, West Virginia, Tennessee, Kentucky, the corner of Ohio, we're sort of on the edge of that mountain range. That's the result of a very ancient old plate collapse. So at one time, the Appalachians, the mountains that you can drive into PA and get into the hills, would have looked more like the Rockies. Big, 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 sharp, pointy, young, aggressive mountains. They are very old hills now. They're worn down with time. But we can go in and we can actually sample a chunk of rock and take it back to a lab somewhere, and through a series of chemical tests, we can tell how old that rock is. How old is that rock? And we know that rock gets laid down, newer stuff on top of older stuff. This is like making a peanut butter and jelly sandwich. You lay down the first piece of bread, you put the peanut butter on it, then you put the jelly on it, then you put the next piece of bread on top of it. You can't put the peanut butter down first. It doesn't work. So we know that new layers get added on top of old layers. So we can tell that if there is a fossil, I'll draw my best fossil fish here, in that layer of rock, and we're able to age, either we can get a chemical test and age the rock near the fish, and we know when it died, or if we can't age the layer it's in, sometimes we can age the layer below it and the layer above it, and we can say, well, it's younger than 10 million years and older than 8 million years. So it's somewhere between 8 and 10 million years old. So we can get this age of death based on geology. Give me the phone, Robbie. So fossils really, they show evolutionary stages. And in the whale, and so this would be what? Not Pachycephalosaurus, that's a dinosaur. Pachycetus. And then this would be Ambulocetus. And here we have, what's the next one? Is it Basilosaurus? I thought there was something. No, there's Rhodocetus. Ambulocetus, Rhodocetus. And then this looks like they're showing a Durodon there. So you see these stages, you see gradual changes. That's what the fossil record can show. So can the fossil record show a lot about the evolution of earthworms? No, because they don't leave good fossils. Can the fossil record show the evolutionary history of every species on the planet? No, because not all of them have left good fossils. But we can put together enough out of the fossils we do have to figure out evolutionary history of some other stuff. The same, this Morphed When Whales Had Legs, was a National Geographic film. They also made one called Morphed From Dinosaur to Turkey. If any of, I'm trying to get it, I'm trying to find a copy of it. But this Morphed From Dinosaur to Turkey looks at the history of birds. And they talk about how turkeys have retained a lot of sort of dinosaur characteristics. So when you sit down on Thanksgiving, if you're eating a turkey, you can think about carving into a dinosaur, because in essence that's what you're doing. Roar! I think it's kind of fun. Okay, so the fossil record is sort of the first piece of evidence for evolution. Prior to a good understanding of what evolution was, prior to Darwin putting forth his ideas, people really did think that a lot of the fossils they were finding were things like dragons. And that if everything was unchanging on the Earth, there couldn't be any species that were extinct, and therefore, these things must exist somewhere. So there would have to be dragons somewhere. Of course, as far as we know, they were wrong. But we don't know about Nessie yet. So there's structural evidence. This is number 2. Structural evidence is the broad sort of overarching category. Structural means what? Really, in the broadest sense, structural just means how it's built. So a structural feature of this building is that there's a central space with wings off of it. It's a structural feature of the building. That there are upstairs and downstairs hallways are a structural feature of this building. So structural evidence is evidence that comes from how organisms are actually built. There are 2 kinds of structural evidence. Okay? 2 kinds of structural evidence. The first one is what we call homologous structures. I want you all to say that with me. You ready? 1, 2, 3. Homologous structures. Okay, you guys can do better than that, seriously. Homologous. 1, 2, 3. Homologous. When we see the prefix homo, what does it mean? Same. Homo means same. Homologous structures are things that appear in different species, but they have the same shape underneath. So if you take a look at your arm, everybody hold your arm up. Has anybody here ever broken their arm? You guys are a lucky bunch. I haven't either. I've known lots of people who did. So there are 2 bones in your arm between your elbow and your wrist. You know that, right? The radius and the ulna. I can never remember which is which. But there are 2 bones side by side. That's kind of a weird arrangement. Why would you have 2 bones when one would do? Well, it turns out, if we look, so there's the human lower arm. If we look at a cat or a dog or a horse or a cow, in that, so, you know, here's the arrangement we have in a human arm. We have these small bones. They're called phalanges. That's your fingers. And you all know that there are multiple bones inside each finger, and you can kind of see them on here. And then you have these little squishy together bones. They're these tiny little bones that look like, I don't know, marshmallows that have been pushed together into a space. And then above that, we have 2 bones. So we've got this really distinct arrangement. These little long bones, followed by the squishy bones, followed by the 2 long bones side by side. Well, if we look at a cat's arm, we have all these long bones. If you look at a cat's paws or a dog's paws, same thing. You have those long bones inside. Then you have those little squishy together bones. And then, what do you know? You have those two bones side by side. Well, if you look at a whale's flipper, you have those long bones. Then you have, you guessed it, squishy together bones. Then you have two bones side by side. What do you know? Well, if you look at a bat's wings, you have these long bones, some squishy together bones, and then guess what? Two bones side by side. Those are considered homologous structures. So the bones of the hand and arm for humans, of cats and dogs and monkeys, and the flippers of whales, the wings of bats. You know that bats are a mammal, right? Bats are the only mammal that is capable of true flight. You knew that? When I was a naturalist years ago, I did a program called Bat Chat in the evenings, and we would go out and look at bats. And I always said, you gotta give a cheer for the home team. They're mammals. They're on our team. And they're the only mammals that are capable of true flight. I would love to be capable of true flight. I think it would be really, really cool to have bat wings. But alas, I do not. Okay, so the first piece of structural evidence is homologous structures. Structures that are in different species and have similar shapes or similar bones. We can look at it and pick out the same kind of bone. What was that structure in the ear that they talked about in whales that only whales have? What was it? I'm thinking of the sigmoid process. So the little tiny piece inside the ear, it's called a sigmoid process, and only whales have it. They said at the end of the film there are over 80 species of whales today. Guess what they all have? Sigmoid process. So it's a little bit different from species to species, but it's a homologous structure. It's a homologous structure because it's something that appears in different species, but it shares a general shape, and it shows or points to the fact that they probably had an ancestor in common at some point. That at some point in their past, they were probably related. We'll stop the notes there. What I want you to do is I want you to take the 10 minutes we have, because I'm tight. I want you to summarize your notes either on paper or open up, and you can even do it on the same project that you've been doing. You can write, you can record if you want to record, you can go off to a corner. But you're going to do a little summary of what we talked about today because you'll have a recall quiz tomorrow. Okay? So you're going to summarize it for yourself.